So you can see the fluid flow by just looking through the glass. You can see the melting inside. If you actually looked at the actual weld, I'm sure you'd have a crack right behind it. You're basically cutting the glass in two, but you can see what happens in the what they call the beam hole. The other thing is, when you look at it, they also weld on aluminum, and they don't explain it in the movie very well, but you have to have the lights down when they're welding on the aluminum. They use an X-ray camera and essentially project through, and so you can kind of see you see this kind of gray image, and then there's a lighter gray because you have this beam hole where the electron beam is coming into the aluminum. You have less aluminum, so it's less dense there. And every now and then, and Chris might have to back it up for you when he plays it, at that spot, there's a little black dot or dark spot, dark gray spot. And what they did is they drilled a hole in the aluminum plate and put a copper wire there, and copper is more X-ray dense than aluminum. And so when the beam hits that piece of copper and aluminum mixed in the liquid, you can see a dark swirl, and that helps you see the fluid flow as the copper mixes in with the aluminum. Okay, so you see a darker swirl. So you have chocolate ripple ice cream, I guess, or whatever going on. Okay, no other questions. Just so that's what you'll see week from Wednesday. Okay, you ready, Chris? Okay. And I'll usually go through some sort of review like this. I talked about how joining combines many of the disciplines in an integrated manner. I don't know if I mentioned, we're going to cover lots of different things from physics to structures and mechanics and things. And you don't have to worry about whether you understand all of it, because to a certain extent this course is just kind of expose you to some of these things. If you ever really need to learn anything, it's best by going out and doing it. I was a student here once, and I never learned anything until I came back. I was exposed to a lot, okay? It's the old fire hose thing. But I never really learned it until I actually had to use it. So, and that's one of the reasons I give you the handouts. If you want to keep them for a few years and you ever find you need to go back and refer to something. Joining has increased the size of things that we can make. It's reduced the cost of things. It's improved the reliability. You find it nearly everywhere. And that's basically where we finished last time. The next board is some of the introduction. I'm going to do some more. But some of the other things, it's not just joining we're talking about. Sometimes we're talking about how to make things. This happens to be a turbine blade. It's a single crystal turbine blade. It's probably about 10-year-old technology now. But this one, well, it's bicrystal now because they took an electrical discharge machine and they basically sliced this thing. They call it filleting in the industry. This turbine blade, if it was a good one, and it's not a good one because it's got a corner ground off, and that's typical of a turbine blade that's been rejected. So no one will put one in an engine that's been rejected in inspection. They grind a notch on it somewhere. So anybody installing these things, if there's ever a corner or a notch ground in it, knows that's a bad one and don't put it in the engine. But these things have an interesting casting technology. Inside, they have all kinds of baffles and air passages. In the bottom, you put 1,000-degree F air as cooling air, and that's because the gases going through the engine of a modern jet are hotter than the melting temperature of the metal of the engine. And you have to cool the metal. Otherwise, if you were to lose your air cooling, which actually comes from the compressor of the engine anyway, so you can't really lose your air cooling unless a hose breaks loose or something, which I guess is good. You would melt your engine. And so what they have to do is they have to laser drill little holes, and these holes are at different angles. It's just a high energy density laser that, or electron beam, it could be either one. And we'll talk about energy densities later. That drills these holes, and then the cold 1,000-degree F gas, relatively cold, because this thing is going to operate around 1,800 F, maybe 2,000 in some of the fancier alloys now, basically forms a boundary layer across the surface, an insulating cold boundary layer to keep this thing from melting in surface. Nowadays, they're getting thinner and thinner walls. The walls are getting down, well, they're down to 30 thousandths, and they're talking about getting them down to 15 thousandths thick. And so it's kind of interesting technology. If that was a good blade, it'd be worth $4,000, approximately. plus or minus. Okay. This is a stator. One of these, let's see, one of these is from a 747, one's from a 757 engine. I can't remember which. But in any case, this is a stator vane. This one's got the same cooling passages. This one doesn't rotate, it's stationary, but it's got the ceramic coating on it. And that, you know, the joining of that ceramic coating is important. And again, the ceramic coating is there because the gases going past this thing are hotter than the melting temperature of the metal that's in it. I passed around last time, but I think it might have been the second class, a piece of the X-33 space plane, did I? Anybody remember?
Yeah.
Okay, this is the second hour. So if people didn't see it, this is a composite structure from the X-33 space plane, and I think I mentioned it to the people in the second hour. But and I think I mentioned that that's basically $10,000 a pound constructed for that composite. So it's a little pricey, but it's a graphite fiber composite, and we'll talk about some of that stuff later. This is just a piece of HY80 steel from General Dynamics Electric Boat. Just a test plate. They actually use this HY80 is 80,000 KSI yield strength, and now use 100 KSI yield strength steel, and they were going to go to 130 KSI yield strength steel until they ran into problems with the Seawolf submarine. So that's just an arc weld and a heavy piece of steel. You can see the heat affected zone etched on the side. I think in the second hour last time I passed around this that people might be interested. For some that weren't there, this is a 2-inch thick electro slag weld in titanium that was made for making titanium submarines. There's not a lot of other applications for heavy section titanium. There are other applications of welding. This is actually not a weld, but this is a metal wood for golfing. Okay, and in order to make these things, you cast them, investment cast them, same way my MIT brass rats made by investment casting. The old lost wax casting. You make a wax model, dip it in a ceramic slurry over and over, then melt out the wax, and then you have a mold. Well, they do that to make a metal wood, and then they have a foot plate that goes on here, and then that foot plate has to be welded on, and then they sand over that weld. They got to get enough penetration in the weld so that when you sand over it, you've got something that the customer can't see any voids or anything like that, so far as that goes. Other types of joining technology, this is a diffusion bonded titanium airfoil. This was a prototype for the F-22 fighter aircraft. This basically has the shape of an airfoil, and it would have been one of the big vanes for the front of the engine. And it's just been sliced through. But this was diffusion bonded. You'll see it kind of is welded at the ends. It's 2 sheets, and there's actually a bonding plane right down the symmetrically down here. And just an example of what's called superplastic forming diffusion bonding. This is a braised heat exchanger. This was from the internal cooled recuperator project for the Navy. The idea is on ships, you have a lot of hot air going up the stack, and you'd like to recoup some of that heat to preheat the air coming in so that you get more efficiency. It turns out when you have a carrier battle group, turns out I guess it's the carrier that has most of the oil for the other ships. And so, but nowadays, because of the types of weapons people have, you have to have your escorts as much as 30 miles away. Okay, and so it turns out a significant fraction of the escort's time is traveling back and forth to pick up oil from the carrier so they keep steaming in the battle group. In fact, I think the numbers I heard were something like 30% of the time you can be off station, essentially traveling back and forth just to get fuel. They could reduce that to like 5% off station and significantly reduce the number of escorts they needed if they could get a more efficient engine. And so they built something that's about half the size of this room as a heat exchanger, and it's a stainless steel waffle shape, and it's got counterflows. There's some small passages and some big passages. So the hot air, I think, goes through the small passages here. The exhaust goes through the small passages, and the incoming air comes through the bigger passages. It's a cross-flow heat exchanger. The problem was when they built this thing and tested it over at Rolls-Royce in England, because Rolls-Royce was designing the turbine, and they had the engine to test it on, it was supposed to last 100,000 hours, and it lasted, so far as I could tell, 2 minutes before it tore itself apart. And the problem with that was, in order to save money, they decided they couldn't do a full stress analysis on how this thing heats up. So they did it in 2 dimensions. In 2 dimensions assumed that the 3rd dimension everything would be symmetric. The problem is if you have something like this and everything flows through it symmetrically, the thermal expansion and stuff will be uniform. No one told the real structure, though, that the gases had to go through it symmetrically, okay? And therefore, when it heated up, it just twisted itself into a pretzel and cracked everything in 2 minutes. They solved the problem since, but they were about to cancel a $300 million program because of that. This is a piece of stainless steel. It's plasma cut. We'll talk about plasma cutting. I guess you saw it if you went to the lab tour. This is a little bit heavier piece than we were cutting in the lab. If you look at this, you'll see it's not quite square as you go around the corners. And the problem is I have heat flow here, and then I turn the corner, and I don't get symmetry around that corner, and that creates some problems. This is a friction weld. Take 2 bars of steel, and you'll see a movie on this, but you spin one against the other. We're going to talk about this, and it heats up, and you fuse them together this way. Most of the drive shafts in your automobiles have the steering knuckle, not the steering knuckle, but the universal joint, you know, the kind of yoke, is welded on to a hollow piece of steel by friction welding. Very fast, reliable process. Also used to join parts of jet engines. When you're joining two $30,000 parts to make a $70,000 part. This is an example of riveting of aluminum and steel using steel rivets. This was done by Chrysler Tech Center to put automobiles together. They built 6 Chrysler Neons before you ever saw a Chrysler Neon. They had built 6 of them out of aluminum to see what the performance advantages were. And the problem is joining aluminum in the automotive industry is not an easy thing. We'll talk about that. You can say, gee, you've been joining aluminum for years. That's true, but not at the cost requirements of the automotive industry. Typical way for welding in the automotive industry is a piece of galvanized steel. There's 2 pieces here. And you come down with 2 copper electrodes, you squeeze it, you apply for about a 1/10 of a second or a 1/6 of a second, about, in this thing, 10,000 amperes of current. And it just melts a little spot. It's called spot welding, invented by Elihu Thompson. Anybody know who Elihu Thompson was? Elihu Thompson was the founder of General Electric, along with Thomas Edison. Thomas Edison had more patents than anybody else in the country. Elihu Thompson was number 2. Elihu Thompson's day job was professor of electrical engineering at MIT. For 1 year, he was president of MIT. And they founded General Electric at a little place up here called Lynn, Massachusetts. The Lynn River Works was the beginning of General Electric company. This is a printed circuit board. It's actually part of a great big printed circuit board, about 2 feet by 3 feet. And it's got, I didn't count them on this one, but this may have about 10 or 12 layers of a plastic that's basically adhesively bonded together, but it has metal grids on it, has holes drilled through it, and you can essentially plate through these holes and make electrical contacts. So you put your chips up here and your passive components and your active components up here on the circuit board. This would technically go into something like these great big circuit boards cost about $2,000 or $3,000 just for the board before you put the components on. Has to be 100% reliable. You miss one connection and the board doesn't work, right? And typically we go to something like a telephone switching system or something like that. It's not your typical Walkman or something like that. It's a bit larger. These are just simple little pipe welds. In this case, for semiconductor gas handling, This one is a nice, pretty fancy one that made up, cut away, so you can see it for a trade show display. But in fact, it turns out these things you'll have when you arc weld, you'll get some vapor come off and you'll get some discoloration. And IBM and other companies used to buy these things from a company, be a $10,000 system, and they just cannibalize one of them, cut it open. If they saw you discoloration, they'd scrap the whole thing and send it back. Okay, so people were concerned how to get it clean. That one's been cleaned chemically. Okay, you don't see anything on there, but some of the types of problems people run into. They were concerned that any particle that got in the gas stream in the semiconductor manufacturers is going to destroy the chips, and so they were concerned about that. This is a composite structure. It has, can't remember, this is zinc, basically some sort of zinc cadmium telluride or something like that. It's a 2,6 semiconductor compound. It's got a little ceramic grid that separates these things, so that this is basically just a kind of a serpentine circuit. And it has aluminum plasma sprayed on the surface as the contact between each one of these little semiconductor chips. This is a thermoelectric generator. You put heat on one side, cold on the other side, the temperature gradient creates a voltage and a current. And you can get maybe 5 watts out of something like this. Very, very reliable electrical power. Not a lot of electrical power, but if you have a source of heat, and you can just put a cooling fin on the backside, you can generate electricity. Why would anybody want this? Well, there's lots of places in remote areas where you can't go and replace the batteries. Let's say you're on the Alaskan pipeline somewhere, okay? Where do you get your, well, actually not the Alaskan pipeline, but a gas pipeline somewhere, and you're in the middle of nowhere. You want to have some sensors to check what the pressure and the flow rate and everything else is, and those sensors have to be powered by something. You don't want to have to send people out there to change the batteries all the time. Basically, you can set this up with a little catalytic platinum catalyst, like a Coleman lantern, burns, and the gas basically can supply the heat, and you get cooling on the other side, and it's a long-term, very reliable battery, if you will. Generate all the temperature difference. Some other things we got in here. This is just a piece of braised scissors. This is part of a medical instrument. They braise on a carbide cutting teeth. Actually, this one is still not carbide. It's stellite, which is a hard cobalt alloy. But sometimes they put carbides on the surface. This is just 1/2 of a pair of scissors. It's partially ground. You can still see where they haven't ground the other side completely yet. This will get a gold-plated handle. It'll be sold to a surgeon for $300. Okay, it's custom medical, right? It's a very high-quality scissor, and with a hard edge, it stays sharp. And you really want sharp scissors when you're cutting on people. You don't want to have to pull a little hard. Another instrument, medical instrument. This is a catheter. If anyone's ever had a relative have a stent put in or something into their heart, or they do non-invasive, well, it is invasive, but it's not open heart surgery in the pull open the whole, crack the breastbone and open up the whole chest cavity. They can just put a hole in your leg, dilate it to about 1/2 inch, try to keep pumping blood in faster as it leaks out, and run this thing up through your leg, up to your heart, okay, through your blood vessel, and they can put little fiber optics on it. This is called the guide wire. This is the one you send up there first, and then the guide wire acts as the thing that carries the other instruments up there. And they can do all kinds of surgery now. Stents are little expandable metal things. So if you have an artery that keeps on collapsing all the time, they now go in there and they basically put this little spring-loaded stent, S-T-E-N-T, in there, and it expands and it keeps the artery from collapsing anymore. It's been wonderful. It's gotten rid of lots of expensive open heart surgery. How do they follow this? Basically, the radiologists are now the surgeons that do this type of work, because they basically have a X-ray camera right there that's taking a shot, and you see about once a second you'll see a new image. or the surgeon basically sitting there on the TV, watching this TV X-ray image of this thing going through your blood vessels and stuff. Now, what's this one like? I mean, this is in a little tube, so it's nice and long. Don't pull it all the way out. It's a pain in the neck to get it back in. But it's stiff back here because it's nothing more than a stainless steel wire coated with Teflon. That's why it's blue. Except at the end up here, the stainless steel wire has been tapered down, and then they wrapped another very fine stainless steel wire, kind of like a spring around it, and it makes a very flexible tip. So you can bend it if you want. At the very tip, you got to make a weld. And if that weld lets go, and it's already up in your body, you have a problem, because when you pull it back out, it's kind of like a roto-rooter as that spring comes uncoiled, and you clean out the arteries, and the person dies. Okay? And you clean out the arteries all the way through the wall of the arteries. It's not good. So that's a fairly high quality, or the weld needs to be high reliability. This is something called friction stir welding. It's the only truly new welding process. When I say truly new, it's fairly new. In the last 10 years, I once applauded for a talk I was giving. In the American Welding Society lists 199 different welding and cutting processes in the back of the handbook. And I went through and counted in the first half, basically from 1880 to 1950, 75% of those processes were developed in those 70 years. In the last 50 years, only about 25% of the processes have been developed. And in fact, in the last 10 years, this is about the only process I can think of that's new. We're kind of running out of ideas of ways to join things. But this one, basically you start with a rod of material, typically, let's just say it could be a piece of steel, and you spin it very fast between two sheets that you want to join together, and you basically, the frictional heat and the stirring action of this rod, you just push it through here, and you machine it down flat when you're all done. A distortion-free, fairly high-strength joint in aluminum. These were made by NASA. Boeing just put in a $10 million line to be able to friction stir weld components for aerospace, but it requires heavy fixturing and some other things. We'll get into that when we get into friction welding in the next couple of days. Here I'll just pass these around. These are ceramic chip carriers. You basically got, just like that printed circuit board that's up there that has like 10 layers. This may have 10 layers, but it's between ceramic and their gold layers. There's different chips in here. These that are in the little plastic things, these are getting kind of old now. These are Pentiums, okay? Maybe I should ask Intel to give me some Pentium 4s now. But they have a little dot on them, which means that the chip was no good. So this is what we call tape automated bonding. This is a plastic tape carrier, and you have about 360 electrical leads going into this chip, and you have to make those connections to the chip, and then you have to make the connections to the package that this thing's going to go in. The package might look something like this piece of ceramic. So the chip might be worth $100. The tab tape might be worth $50, and the chip carrier might be worth another $50 or $100. And that's why you're going to pay $200-300 for a fancy chip. The problem is some of the other chip carriers are in there for memory chips, and nowadays, as you know, you can buy memory chips for $2, right? Memory's getting real cheap. And that's just because the world hasn't learned the same thing that they should have learned over and over again. The steel industry, for example, overbuilt capacity. This actually sort of is this digression. After World War II, the United States had 75% of the world's steel-making capacity. Why? We bombed everyone else's industry. Okay? There weren't a lot of bombing raids over Pittsburgh, okay, during World War II. At least not of the enemy, okay? Maybe some GIs dropped some by accident. But in any case, we own 75% of the world's steel-making capacity in 1945. When I went to work with a steel company in the early 70s, mid-70s, we had 25% of the world's steel-making capacity. We now have 10% of the world's steel-making capacity. The last integrated steel plant that was built by a company was Bethlehem Steel, Burns Harbor, between mid-1960s and early 70s. Bethlehem Steel just about went bankrupt doing that, because back then it was about a $5 billion plant. To build an integrated steel plant today is probably $15 billion. There's no companies that can afford to do that. However, we build one of those in the world somewhere every year now. Okay, it'll turn out 10 million tons of steel. But it's always backed by a country nowadays. We don't build integrated steel plants. The last one in the United States was Burns Harbor 35 years ago. Korea's built 2 since then. The Korean Steel Company is now the world's largest steel producer. Korea doesn't use all that steel. They ship it to the United States. Okay? And so 25% of the steel in the United States is imported now, because we are still the largest, well, China may be the largest market for steel now, but it's a lower quality steel. Russia used to produce, or so former Soviet Union used to produce more steel, but it was all low quality. So, as one of my colleagues said, they were very proud of the fact they did this remelting process, which is a very high quality upgrading process, and they remelted 80% of the steel. He says that's because it's so bad to begin with, they had to upgrade it. The quality was so poor. But they were proud of it, that they were redoing all this extra work to refine it better. But it's only because the first stuff was so bad you couldn't use it. Anyway, so the world has 25–30% overcapacity, because some country decides we're going to be an exporter, and another country decides we're going to be an exporter. And all of a sudden, the next thing you know, the world is only using 70% capacity of what we've got, and everybody's cutting each other's throat. Well, the exact same thing happened in the semiconductor memory business. Okay, Korea, and Taiwan, and Singapore, and Malaysia, and all these other countries decided, okay, the United States was making lots of money in semiconductors, and a couple of the Europeans were, and so they were going to be the next great semiconductor manufacturing firms. So they built capacity, again with government money, okay, and now they're operating at 60–70% capacity. And the good news for you is you can get 128 kilobytes of RAM for 49 bucks, right? Megabytes of RAM for 49 bucks. And it's going to stay that way. There'll be some fluctuations, but they just built too much capacity. So we have another war, bomb them out again. And actually, you know, to say that kind of tongue in cheek, there is some truth to that. When we had world wars every 25 years, there was a certain advantage for industry, because you got to start all over again, build new equipment, you weren't still using old plants and things. We haven't had a major war that was going to destroy a manufacturing nation in quite a few years, and therefore there's some interesting infrastructure things going on. Okay, so those are some of the kind of joining's ubiquitous, all kinds of different fields, and we're going to talk about some of the different things. Another reason welding and joining is an important thing to study is because it's a relatively large fraction of the manufacturing cost, and it comes near the end of the process when the cost of scrap is high. You've already got 80–90% of the value in the part, and if you screw it up when you join it and you can't fix it, then you've got a serious problem in terms of the cost. It results in many failures, and some of them quite notable failures. I remember when the space shuttle, my students came in and said the Space Shuttle Challenger just exploded. I mean, this was a half an hour after it occurred, and they came rushing into my office, and the first thing I said, I bet it failed at a weld. And I was wrong, but it did fail at a joint. Okay? Why do things fail at joints? Well, the corners, okay? And the corners are where the stress concentrations are. So it's not the weld inherently that it's at the most highly stressed location. Oftentimes the joint is inferior. I can't make a joint in that composite from the X-33 space plane that's as strong as the carbon fibers. I just can't do it. And so I have to do all kinds of overlaps and doublers and things like that. Those things add weight to things, but it increases the joint's and sometimes the joints just can't meet the strength of the base material. Particularly as you get to advanced materials. I can meet the strength of HY80 steel or HY100 steel, but as I go to higher and higher strength steels, I have a harder and harder time getting the welds to match the strength of the base material. And as you get to composites or ceramics and things like that, it gets to be very difficult to match the properties. There's a bit of a problem. It's a problem for some people, it's not a problem for me, but it's not a problem for me because it gives me lots of consulting work. There's not a lot of people that know a lot about the whole field of welding and joining. For example, in the former Soviet Union, now in the Ukraine, there's the Turbine Welding Institute. And the Soviets did lots of things for political reasons rather than economic, scientific reasons, but it turns out Professor Paton's father was a hero of the Soviet Union in World War II because as the tanks got wiped out by the Germans, he would go out there and use the welding technology to get the tanks back in service. Right? So after the war, he was a hero for having kept the tanks on the battle lines, and he and his son after him became heads of this Paton Institute in Kiev. The Paton Institute used to train 5,000 welding engineers every year for the former Soviet Union. The United States has Ohio State University. It's the only school with the Department of Welding Engineering. They graduate about 40 welding engineers a year. Okay? It's also Lutherno in Texas, and they graduate another 20 or 30. But nonetheless, if you look at welding as a field, we tend to do disciplinary. We train someone as a physicist or a mechanical engineer or a metallurgist or whatever, and then we send them out to work, just like I did. I learned welding when I went to work for Bethlehem Steel, and they said, "You're a welding engineer." Okay, I'd worked on superconductivity before. I always said, "Well, high currents, that's a common thing. We use hundreds of amps. That's something that's similar between the two." But in fact, there are a number of failures and problems that occur because you take someone who is disciplinary trained and really hasn't gotten into the whole field of welding and joining.
Zoom those front lines a little bit.
Yeah. How's that?
Good.
The last is welding often places constraints on the use of a new material, or your ability to join it places constraints. The composite structures, we've talked about that a little bit. Certainly major constraints because I don't have the joining technology that can match the properties of the base material. It turns out aluminum in automobiles. Aluminum is not exactly a new material, but it's sort of a new material for automobiles. You say, well, what do you mean? One person said to me, what was the Nissan car? The
E280.
280Z. It's one of the Z's, okay. Was an all aluminum body. Of course, now you got Audis that are all aluminum bodies. But it turns out, for those little spot welding process, and we'll talk later about why people use spot welding, but it's the cheapest welding process for joining sheet metal. It's very fast and very inexpensive. In the automotive industry, it costs about a nickel, maybe a dime, but order of magnitude, you're talking about a nickel per weld. Okay? You can get in steel, before those copper tips that are carrying the 10,000 amps wear out, before it had a spec, you had to get 2,000 welds before you had to replace your copper tips. Well, it turns out for the 280Z, they were on aluminum, they were getting 40 welds per tip. If you had to go to a modern 250,000 car assembly line, where you build automobiles, and it's 250,000 cars because they have about 60 seconds per station. Okay, the line moves, stays there for 60 seconds, or maybe it's moving continuously, and the robots kind of move with it or whatever. But basically, about 60 seconds per station, and the robots or the people are, putting the bumpers on or whatever, and the welders, the robotic welders, have 60 seconds at a station, and then they move to the next one. Well, you figure that out, and that's about 250,000 cars a year, based on the 60 seconds per station, and that's some plants, for various reasons, can get up to 350,000 maybe, but you're kind of limited to something on that order. And you're going to put, as I often say, let's see, how do I phrase it? There's 3,000 spot welds in the average automobile because you need 2,000 good ones. Okay. They're not all high quality, but they're cheap. Well, if I went to a 280Z and I wanted to make, we didn't make 250,000 of them a year, but if you put them in a plant like that, in a high volume plant, and you had to stop every 40 welds, you would lose half your production in that plant. Okay? Because you'd have to stop and change the tips. 50% of your time in that $5 billion plant or whatever would be changing electrode tips. Well, all of a sudden, what was a nickel times 3,000, which is $150 worth of welding, becomes, you know, $2,000 worth of welding because of the lost time on the line or whatever. So it turns out welding aluminum is not a trivial thing. I think the Audis are like 40 or 50,000 vehicles a year. No one has really started building a high volume, I'm talking 200,000 units a year, all aluminum production vehicle. And it is primarily because they don't have the welding technology at the cost to do it. You obviously have the technology to build the car, but not at the cost of a high volume automobile. Anybody, you know, I remember people say, well, we're building all aluminum Audi. I said, yeah, well, anybody who's paying $50,000 for a sedan, you know, only no bigger than a $15,000 sedan, anybody can afford to add a couple $1,000 worth of welding to it, right? If you're going to sell it for $50,000. $15,000 car, you can't just add a couple $1,000 to the welding cost. Okay, so there's often constraints. Okay, any questions? We now finish the overview. Now let's talk about fundamentals of bonding. I'll pass this out rather than draw this on the board. Pass those back. This is the we'll draw it on the board. You'll have a copy anyway. If I want to bring two atoms together, I can plot the energy versus distance, and I'll get something. If I go to a physical chemistry book, something looks like this. If I have an atom right here, and another atom way over here in space, and I bring them closer and closer together, the atoms, if they want to form a solid or a liquid, have to have an attractive force. Okay? So actually, it turns out the derivative of this, dEdr, is equal to the force versus radius, and the force is going to look like that. So this is an attractive force and that's a repulsive force, where the force is equal to 0 is the equilibrium spacing between the two atoms. Right? They're going to come together until they find some equilibrium spacing. If you try to squeeze them closer together, the positively charged nuclei are going to want to repel, right? So that's what the repulsive force is all about. It turns out this spot here, if I call this distance A0, where's A0 on here? Down here, right? So this has got to be dEdr is equal to 0, which is the force. The slope is 0 down here. So A0, the interatomic spacing, is right there. Okay? So it turns out, unless I'm talking about a gas, and a gas, there's no close attraction between things, the atoms, because they're about 10 A0 apart at atmospheric pressure, temperature, if you go through and calculate the relative density. By the way, how would you do that calculation? If I told you that the average gas has 1/500th or 1/1000th the density of the liquid. So if I'm talking liquid oxygen versus gaseous oxygen, and there's 1/500th difference in their density, how did I calculate that they're about 8 to 10 A0 apart in the gas? Yeah.
The volume of the gas is, per mole of gas is what, 22.4 liters, and you can calculate what the volume of the gas is, the angstrom, or not angstrom, Avogadro's number, how many molecules are in there.
I can do it that way.
Calculate out, you know, what.
There's a quicker way though. I take the cube root of 1,000. Okay. A large part of what hopefully you'll learn in this class, you're absolutely right. And the first time I ever did it, I did it the way, I started to do it the way you were doing it. I thought, you know, there's an easier way to do this. When I used to teach sophomores thermodynamics, I used to give a quiz. I learned after 2 years not to do this. Student hated it. That it was an hour quiz, and if you went through and plugged through the way they've always taught you to do problems in school, you could solve the whole, I could take that quiz and I could do the numbers in 20 minutes. I used to figure if I could go through that way and do it in 20 minutes, then the students could do it in 50 minutes. Because I'd written the question, I knew exactly how to approach it. I mean, most of the time it's figuring out how to approach the problem. You know, so I had written the question, I knew how to approach it, but chugging through the numbers might take me 20 minutes. I used to write quizzes that you didn't have to put down any work. You could just read the question and stop and think and just write down the answer. I mean, it might be writing down the cube root of 1,000 is equal to 10. Okay, and what I learned is only 1% or 2% of the answers ever came back where the student actually stopped, thought about the big picture, and came up with a simple solution. And then I go and I explain it to them the next day of how, you know, you didn't have to do all this other work. And I found I just be frustrated when students don't end. So I quit giving quizzes like that. But in fact, as an engineer, you need to kind of unlearn a lot of what you've learned. You need to know what the principles are, and so what you've learned is an important thing. But to kind of go to the next level of doing these things, you have to figure out how to make simple approximations. Okay? So if I know the relative density of the liquid and the gas is about 1/1000th or 1/500, I know that the difference in interatomic spacing is a factor of 8 to 10. Okay? Now, if I look at this plot, if I go to a chemistry book, it turns out this is about 3A0 out here, where this thing is getting down to almost nothing. So the attraction between two gas molecules in the air is zip. Okay, I mean, the force of attraction at 10A0 way out here is essentially dropped off to 0. There is no force of attraction between the gas molecules. They don't even see each other. They have no effect on each other. And it turns out if they're naturally a gas at that temperature and pressure, even if they come together, there is no significant force of attraction. Certainly their kinetic energy is going to be greater than the force of attraction. Okay? So when they start to come together with enough momentum, they just bounce apart. Now, in a condensed phase, it's different. In a condensed phase, things want to bond. They want to come together, and they want to stay together. Now, I can go through, and chemists have measured these types of bonds and their typical strengths. And if I go to my notes, I can write it down for you. If you go to a physical chemistry text, now this is the kind of approach a high school chemistry text would take. What are the types of bonding? There's ionic. You've heard of ionic, right? And the energy of an ionic bond is 1 to 3 electron volts. There's covalent. And it also has a typical strength of 1 to 3 electron volts. Anybody know why I use electron volts? I can convert that to joules if you want. An electron volt, let's see, 1.6 times 10 to the minus 8, 19. Okay, electron volts per joule or something. Or joules. Anyway, a lot fewer electron volts. Anyway, let's see. There's covalent, ionic, metallic. There's also, these are called primary bonds. And they're on the order of 1 to 2 electron volts. That means that if I have an atom here and an atom here, and I actually, in ionic bonding, transfer an electron between the two, the exchange energy is on the order of 1 electron volt. There's about 1 volt or 3 volts of energy change per electron that's transferred. If I have a divalent, well actually I can have, you can just think of it as single valent, divalent, or trivalent, okay, in terms of the strength of the bond. It's not quite that simple, but nonetheless. There's also hydrogen bonding, and hydrogen bonding has a strength of about 1/10 as much. There's also van der Waals, And van der Waals is basically just an electrostatic attraction. It's less than hydrogen bonding. Some people like to say that hydrogen bonding is just a special case of van der Waals. And in fact, that's probably true. But the chemists like to distinguish it because it is so much higher, and it actually changes the physical properties of things that have hydrogen bonding as compared to things that have van der Waals bonding. You know, ceramics are ionic or covalent. Semiconductors are covalent. Metals have metallic bonding. Van der Waals bonding is found, actually, let's go to a polymer. A polymer has a backbone chain of covalent bonds, and between the chains you have van der Waals bonds. So how do I get Kevlar, wherever that X33 space piece is? That honeycomb core is made out of Nomex, which is another, not DuPont's brand, but someone else's brand of Kevlar, if you will. And Kevlar is very strong because they align all the backbones of these polymer chains in one direction. And they talk about Nomex or Kevlar are stronger than steel, but only in one direction. Okay? And the way they do it is they extrude the plastic in concentrated sulfuric acid because that's the only solvent for it. It tends to be hard on the tooling. They tend to make the tooling out of platinum, which makes that's why Kevlar is sort of expensive, right? Because you have to use things like platinum tooling or nickel-based tooling, but it's expensive in any case. Anyway, you align those fibers in that direction. If you want to make a nice long fiber, it's stronger than steel because I have covalent bonds that are stronger than the iron bonds, and we'll talk in a second about that. But between the bonds, if instead of extruding it, getting everything to line up, I just made some Kevlar and just let all the strands or backbones of the covalent polymer in all kinds of different directions, and I try to pull that apart. All I have to do is pull apart a van der Waals bond. Well, the energy of that van der Waals bond is 1/20th the depth of this. I mean, the electron volts we're talking about is the depth of this thing, okay? That's delta E of bonding, and that's what the electron volts I'm talking about. Let me go back and just point out. Anybody know how to get the conversion from electron volts to joules? Aside from remember, it's 1.6 times 10 to the minus 19.
HP 48.
HP 48. Okay, good. You go to Little Pack. Just like I've learned, students now do all their essays on the web. But anyway, it turns out Avogadro's number, which is 6.02 times 10 to the 23rd, divided by Faraday's constant, which is 96,500 coulombs per mole, will end up giving me the amount of charge. And if I divide all that, I should get something like 1.6 times 10 minus 9 times 10 to the 9. No, I get the inverse of that. I get something like 6 times 10 to the 20th, which is 1 over that is 1.6 times 10 minus 19. Avogadro's number of electrons is equal to the Faraday constant. Faraday constant is 96,500 coulombs, which is number of electrons per mole. So there's roughly 100,000 electrons in a mole of atoms, and if I divide by Avogadro's number by Faraday's constant, I'll get the conversion. There's some simple little things like that that are sometimes useful. Okay, so I've got these different types of bonds, and I want to know what the force is to pull these things apart. If I go through, and the handout I handed you came out of this class a couple years ago when I was telling students about surface energy, which we're going to get to in a little bit, and I told them that fundamentally, if I have a bunch of atoms in a solid and I pull them apart, that will give me a theoretical strength of 2 to 3 million psi. And one of the students says, well, how do you calculate that? So I went back after class and I did the problem. Okay, so now I'm handing it out to you. Basically, you start with the Leonard-Jones potential, and you say, well, all I have to do to figure out if I have two atoms together here, is I just have to integrate this, F dot dr, and that's the energy necessary to pull those things apart and separate them if they're bound together, right? And if I do that, I end up with some number that's 1.3 times 10 to the 10th newtons per square meter, which is about 13 gigapascals, which is about 2 million psi for a typical surface tension of iron. Okay. Now we know people in the 1950s grew little iron whiskers and got 2 million psi pulling that iron whisker. Anybody here from Rice University? There's a Nobel laureate down there who discovered buckyballs and then carbon nanotubes. He did this calculation. I mean, it took me 45 minutes to do it, and he's gone around the world now telling people that carbon nanotubes will be stronger than anything ever known before, except that metallurgists knew it 50 years ago, and it took me 45 minutes to figure out how to do this calculation. But he's gone around, and they built new buildings and everything else down there. This guy Smalley is a wonderful peddler. He also won a Nobel Prize for discovering buckyballs, which is an interesting thing. And he's telling people, well, we're going to build everything out of carbon nanotubes. Well, you know, people tried in the 1950s to make composites out of iron whiskers, which have 2 million psi. But they couldn't do it because they're too expensive. Right now, buckyballs will cost you $10,000 a microgram or something. I mean, you know, yeah, you can get them. So why is steel not as strong as 2 million psi, if it's made out of iron? Well, the reason is metals tend to have what we call dislocations. And in a dislocation, I can have a whole sheet of atoms, but that sheet of atoms don't all break all at once. I'm not breaking the whole surface area in every atom across that surface all at once. I basically set up a dislocation in the crystal, which is an imperfection in the crystal, and that dislocation essentially breaks one line of atoms at a time. And I can do the same thing and teach you how to tear a telephone book in two, except you can't do the Verizon telephone books. They now have polymer reinforcement in the paper. But I can use MIT telephone books because they still use the cheap stuff. Okay? But all you do is you set up a dislocation in the paper. You set up a dislocation by just bending it sharply. The inner radius of curvature is tighter than the outer radius of curvature, right? I then grab it with my thumbs, and now I've set up a dislocation. The top sheet is tension, and the bottom sheets are not. And unless MIT started polymer reinforcing these, this worked a lot better in the old days. But you basically rip one page at a time until you get a notch in it. And these are polymer reinforced now. Anybody find any pre-1998 MIT phone books? It's a lot easier. Okay, but basically, you can rip telephone books in two because A, paper's brittle until they start making a composite out of it. And you basically rip one sheet at a time by just breaking the background, okay, of these things. Okay? Essentially, a dislocation goes through a metal in the same way. I can break the metal or cause it to deform at a much lower stress, okay? Because I'm essentially only breaking one load of atoms at a time. Okay, so I gotta let the rest of you go. We'll break to 3371.